Hello everyone. Thank you for joining. As you guys all guys know, JWoC has phase two has already started and is coming to an end in 4 days. So if you guys haven't started contribution yet, you guys can still do that. You guys have the chance to do that. So welcome to the session today. So today's session is related to machine learning and deep learning. So I would like to introduce you all to our speaker today, Purbayan Kar. He is currently a research engineer at Sony Research India and has several publications in reputed journals of organizations like IEEE. So he will share his experience and how to start. So Purbayan, welcome.
Thank you.
Mike is over to
Yeah.
you.
Thank you for the warm welcome, Atri. Yeah. So can I start the session?
Yes, brother.
Okay. So today I will talk about semi-supervised object detection and facial landmark detection. So these are very popular topics in deep learning domain. So I will give a very brief overview of how these topics pans out, and I will not go into much details because I am assuming most of the audience is from first, second, or third year. So I won't go into much detail. But by introducing these topics, I will try to explain various aspects of deep learning, go into nuances of that topic, and eventually try to answer some of your questions at the end of the session, which you might have. So the agenda of this talk will be first I will talk little bit about myself. Then I will talk about semi-supervised object detection. So to understand this topic, we have to understand some internal topics, which are what is supervised learning, unsupervised learning, and semi-supervised learning. I will also talk about some computer vision tasks specifically because I myself is a computer vision researcher. So I will not go deep into machine learning or NLP domain. This talk will mostly focus on computer vision topic. So if you want to keep me talk about other NLP and ML talk, that will be of some other session. But for this session, I will mostly focus on computer vision tasks. Then I will talk about data imbalance, then data augmentation, knowledge distillation. So after you get ample idea about what these topics are, then I will discuss one of my paper which combines all these topics together. Then I will talk about facial landmark detection. And to understand this, I will talk about Siamese network architecture, what Siamese network is. And then I will also talk about another paper of myself which introduces Siamese network into facial landmark detection domain. And finally, I will do a Q&A session. And at any moment, if you have any question, just stop me or you can ping in the chat so I can give you answer to the following questions that you have. Yeah. So about me, I started my BTech in CSE from Jalpaiguri Government Engineering College from 2018. At the beginning of my third year, I got a student fellowship in Indian National Academy of Engineering, where I worked with Professor Vidyut Baran Chaudhary of Indian Statistical Institution on a paper which was published in an IEEE journal. At the very next month, I got an internship in an healthcare startup called Origin Health. I was working as a research intern there at their R&D. So we were working on fetal ultrasound images and the measurement of various structures in fetal ultrasound images using deep learning techniques. But I my stint there was not very long. I stayed there for only 2 months because I was not enjoying medical imaging. So medical imaging is not for me basically. So I switched. I applied at Sony Research and I got into Sony Research India as an intern at August 2021. So there I worked on various topics and in June 2022 I graduated from my college and September onward I started working at Sony Research as a full-time employee. So you have seen I have work experience at Sony Research as an intern for almost 1 year because I couldn't join there at full-time before my graduation. And currently at Sony Research, I have been working for more than 2.5 years. So my research interests are specifically in computer vision. So I started my entire journey in deep learning from computer vision only. So computer vision, deep learning, these are my research interests. Also worked on remote sensing. I like designing optimizers, and I have quite a lot of expertise in semi-supervised learning. So I would like to introduce you to some of my works at Sony Research, what I have done there, and what you audiences who might be having interest in research domain or go into deep learning, machine learning. So you can get an idea what kind of task you might be able to do when you get into industry. So first task that I did there was emotion recognition in conversation. So this is snippet from a very popular TV show called Friends. So there we have multimodal data where we have audio, we have video, and we have corresponding transcript. So my task was to predict the emotion of a particular character fusing these three modalities together. So this can be used in various aspects into Sony's internal business. How much like the audience are liking a character based on his or her emotion. Based on that, the producer or director might generate the next episode. So this was a topic that I worked on, and we also published a paper for the same in CVPR. So the next thing that I worked on was on content moderation. So I have to detect some particular objects which was obscene to be broadcasted on TV. So I had to detect cigarettes, alcohol, or profane words, any such kind of obscene things, and then I have to blur that part. So here I have not shown you the blur part. I have shown you how I am detecting all the objects inside a scene. Uh, so my next task was very interesting and it was very new at that time. It is audio-visual speech separation. So to give you understanding of what this topic is, I will first play a video. Just let me know whether the audio is visible.
Make it quick. Yes, sir.
Is the audio
Yeah.
audible or three? Okay. So
Yes, sir.
just I am playing this video. Just say this.
Malik, before people were pulling their pants down, did we still have a strong police presence in the same yes, position yes, we did right now? Yes, we did, sir. Yes, we did. Yes, we did. But that was then, and this is not. That's my point. All right. Individual choice and responsibility. Every single person in this country has a choice to either behave like a criminal or they have a choice to behave like a reasonable person and carry themselves with respect. I wish we had more time because I know this has hit a nerve with everybody.
Okay. So this is a snippet from a news debate. So we encountered this problem many times in current scenario that in debate or any such kind of like conversation, all the people start talking together. So we as an audience has problem to understand who particular is speaking and what he or she is speaking. So my task was to separate out the audio of a particular speaker and completely mute out other audios. So if you see this result, only this person is will be speaking only, and other audios will be muted.
Make it quick. All right. Okay. I wish we had more time because I know this has hit a nerve with everybody.
And let me show you another example of this person speaking.
Yes, sir. Yes, we did. Yes, sir. Yes, we did. Yes, we did. Not. That's my point. Why not choice? Individual choice and responsibility. Every single person in this country has a choice to either behave like a criminal or they have a choice to behave like a reasonable person and carry themselves with respect. I wish we had more time because I know this has hit a nerve with everybody.
Okay, so I hope you understand what this topic is. I'm not playing these two videos. So basically, if you want to focus on a particular person, this algorithm can focus on a particular person and mute all other audios. So the application of this thing in media domain is very evident. So we can use this in debates, news debates, and any other such kind of source where there are multiple person are speaking. So this was one aspect, and this is still in the research stage. So there is lots of improvement on this. Okay, so my next work was automatic lip syncing. So let me first play the video to you and then I will explain you what this thing is.
Are everything to me, no matter what's going on in my career. And everyone who's ever hired me, Luc Besson, who gave me my first job when I was 11 years old. My
Yeah, so this is Natalie Portman giving her Oscar-winning speech. So now my task was to sync Natalie Portman's lips to any particular English audio stream. So let me play this video.
I am Katrina Kaif and I am a better actress than Natalie Portman. I have done multiple super hit movies and I have won multiple Filmfare Awards.
As you can see, like we can sync Natalie Portman's lip to any particular audio. And so this is very interesting topic that we are currently working on. But the audio that you see, that is not my work. That work is from audio teams that they have to particularly give me similar voiced audio of Natalie Portman. My task as a computer vision researcher will be to properly lip sync Natalie Portman's or any such kind of actors lips to particular audio. And this is again in research stage. There is lots of room for improvement. But again, I wanted to showcase this work to you. Yeah, and another very interesting work is production ready facial de-aging. So again, let me play the video first. This is Akshay Kumar at his current age, I think 56 or 57 years old currently. Let's see the video.
उसको बढ़ाते रहो बहुत ज़रूरी है अरे बाप रे इतने सारे लोग लाइव आ गए थैंक यू एवरीवन बट
Okay, and now see this video.
उसको बढ़ाते रहो बहुत ज़रूरी है अरे बाप रे इतने सारे लोग लाइव आ गए थैंक यू एवरीवन बट
Yeah. So this was Akshay Kumar, DH to 25 years old. This was Akshay Kumar at his current age. So these kind of works have been done multiple times in Hollywood and Bollywood by de-aging actors, but all of them were done using VFX or makeups. So we are currently trying to achieve this using AI-based algorithms to do this in production stage. So I'm not actually sure whether this have been done using AI in any other like any other movies. In Hollywood, I have no idea, but in India, I think we are the first one to do this using AI, not using makeups, not using VFX. So it will reduce lots of efforts and time from VFX part and makeup part. So this was another interesting project that I was working. And now, yeah, so this is my Google Scholar profile. So these are some of my research papers that I have done in past 2 3 years. And these are my co-authors, like very distinguished co-authors with whom I have worked. So if you have time, you can like read some of my papers. Yeah. So now I will come to the main discussion of this topic. So first I will discuss about semi-supervised object detection, and I will also discuss my paper, which is revisiting class imbalance for end-to-end semi-supervised object detection. This was published in CVPR workshop in Vancouver, Canada, and we presented this paper online. So to understand this paper, we have to understand some of the basic topics of deep learning. So first is what is supervised, unsupervised, and semi-supervised learning. So in machine learning, we call supervised learning when you have corresponding data and labels for all the data. So machine learning model is kind of a black box. You need data to train the black box. So you need labels for the data to understand the black box, what a particular image or data is. So for as I have already said, I will be explaining computer vision topics. So here are some images, and here are the localization of images where that particular face is. So for all the images in this data, we have all corresponding labels. So when we have this kind of data, we call it supervised learning. Unsupervised learning is when we have only this data. We don't have any corresponding label for that data. Then we call that process unsupervised learning. So then you might be thinking like how can we learn from the data when we don't know what the labels are. So at this time, what we do, we learn inherent characteristics from the current data. So let me explain you in a very naive way. This is very similar to we as a children learn during our childhood. So let's say like you take a 4-year-old boy to a zoo, then you show him zebra, you show him giraffe, and you show him an elephant. So he doesn't know the names of that particular animals, but he observes what how those animals look. At the very next day, you ask him which were the tallest among them. He will be able to point you that it was giraffe, but he doesn't know that the name of that particular animal is giraffe. But he understands how their latent aspects are, how their characteristics are. So this is unsupervised learning. And semi-supervised learning is when you have corresponding data, you have also the labels, but not for all the data. So you have partial labels. So this is very interesting, and we often use this thing into industry because annotating all the data is very time consuming and difficult. So when you have partial amount of annotated data, how can you use some algorithms or some techniques to use that partially annotated data and achieve the same accuracy or same level that you will be able to achieve using supervised learning? So this is very interesting topic, and I think there are many research around this, and in future also this will be in very trend. So yeah, till now, if you have any question, I will stop for a few seconds and then I will move.
If you guys have some queries, you guys can ask in the chat box.
Sir, hello, am I
Hello.
audible?
Yes, yes,
Yeah.
you are on.
Sir, will you share more about your research, sir, emotion recognition and conversation?
Okay. So in these slides, I don't have much data in that, but yeah, I will talk about this a little bit at the end. Yeah.
Okay, thank you, sir.
Yeah.
So, Vivanda, there is some one question.
Yeah.
So,
Is
if
it
you can,
possible to do supervised learning with large sets of data or only small sets of data? Okay. Yeah. So the general notion is you have small sets of data, then your accuracy will be low because the model is not exposed to much amount of data. So if you have larger data, then your accuracy of the model will be very high. So this is a very interesting question actually. How can we do supervised learning in small sets of data? And I will answer this in subsequent slide. It's a very nice question. And yeah, so if you know the technology behind ChatGPT, it was trained practically on the entire internet. So yeah, that's another food for thought. But I will answer this question in subsequent slides. Like how can we do supervised learning using small sets of data? Yeah. Okay, so if we don't have any other question, let me move to the next slide. So now I will like very briefly explain for beginners like what are various computer vision tasks and what basically object detection is. So first I will talk about little bit about classification. Classification is when you have an image, you have to classify what is inside the image. So here the model classifies there is cat. Very simple. It has been doing. People have been doing this for ages. Then the next little bit difficult task is classification and localization. So now you don't need to just classify what is inside the image. You have to give me exact location where inside the image at the particular object is. So this is classification and localization. So specifically, you have to give me a bounding box around that particular object. So now if we move a little bit and make it a little bit difficult, now you have multiple different classes of object in the image. Then you call it object detection. So then we don't call it only localization, we call it object detection. Like here there is dog, there is another cat, there is different breed of cat, and there is a duck toy. And now people also do some crazy thing called instance segmentation, where you classify every pixel of that particular image. So here we classify every pixel of this portion, this laser pointed portion is of dog, this is of cat, and this is of duck. And these things are extensively used in autonomous driving. You might have seen autonomous driving technology in Tesla car or ADAS camera-based ADAS technology in other cars. They all use instance segmentation. So where they segment each and every portion of the road visible So they segment pedestrian, they segment car, they segment road light signals. Everything is done using this technology, instant segments. Okay, I hope this is clear to all. But for this presentation, my motive will be only to explain you object detection. So first, we will start with classification and localization and how you can do this. So classification is very simple. So you have, let's just see number of classes. The classes may be cat, dog, horse, and then you have to just predict whether it is cat or not. So you apply a model you train using corresponding data and you predict this is cat or not. But for localization, to create that bounding box, what we do, we predict 4 points, which are x, y, w, and h. So if I go to the previous slide, x, y will be the middle portion of this object, and w and h will be width and height of the particular box. Middle portion, width, and height. So if you have all these components, you will be able to draw that bounding box around this particular object. So this is localization. So how will we do localization? Localization is not a classification problem because you are not classifying whether it is cat, dog. It is a regression problem. What do I mean by regression? In regression, you predict a matrix, a set of points that we call regression, and we calculate corresponding loss for that. So I hope most of the audience are aware what loss is. But if you don't know, loss is a term that we penalize the model that this much amount you are right, this much amount you are wrong. This is the term by which we penalize the prediction of the model. If it is correct, the model is predicting correct, the loss will be low. If the model is predicting incorrect, the loss will be high. So now we get the four box coordinate x, y, w, and h, and we have corresponding label for that into our dataset. As we are currently doing supervised learning, not moved into semi-supervised here, we will calculate the loss and penalize the model correspondingly. So how will you do that? Basically, you nowadays we don't design neural networks by ourselves. We don't do by scratch. We have popular models called AlexNet, VGGNet, GoogleNet. The black box that I was talking about, you can take any one of this, predict the class code, and calculate a softmax loss. Softmax, don't get worried. Softmax loss is another variant of loss. I won't go deep into this. But to do classification and regression both, you need two heads. One is a classification head that will predict whether it is cat or not. The regression head, which will predict me the 4 points. So you have to add these two head components after those popular networks that I just mentioned in the previous slide. When you get this box coordinate, you calculate the L2 loss, penalize the model to backpropagation. Backpropagation is nothing but making the model aware of what it learned at a particular iteration or epoch of the training. So this is the till now, this is the way you train the model. But at the inference time, you use both. At the inference time, I mean at the testing time. Inference means testing. When you are testing the model with a particular image, you have to use both the head together. One head will give you class score. If this is cat, the score for the corresponding cat class will be highest, and the box coordinates. So this is the very high level overview of what classification and localization will look like. Yeah, so anybody has any question till now? So this is the very high level overview of object detection.
So, Wanda, we have one question. What is the process of creating a model, then and training, just like object detection in images?
Okay. So as I said, like do models, like make models scratch from now. There are very popular models which have been already trained on a large amount of data. So they are pre-trained models and they work extensively good on any kind of images. So these are AlexNet, VGGNet, and GoogleNet. They are usually trained on ImageNet dataset, which is a very popular and large dataset. So you use any such kind of model. So for instance, just assume this is VGGNet. You employ VGGNet, but VGGNet won't give you final output. It will give you features of that particular image till this portion. Then you have to employ these two heads. and these you have to design by yourself. These are some fully connected neural networks. Uh, I don't know if it you are able to understand because fully connected layer, these terms might be little bit difficult for newcomers. But for now, let us assume like these are another black boxes which we employ upon LXNet or VGGNet, which will give me classification score or regression score. Regression score means those 4 points X, Y, W, and H, and classification score whether it is cat or dog.
Okay, so
Is
I
it
guess
okay?
your doubt is clear. Okay.
So now I will talk little bit about data. Like someone asked, like what will we do when we have very small amount of data? So a very important thing to like keep in mind when training deep learning models or machine learning model is the data. Your data has to be balanced. If your data is not balanced, your model prediction will be skewed or biased. What I mean by balanced is, let's say you have 10 classes in your data. The classes may be cat, dog, horse. The number of images for those particular objects in your dataset should be more or less same for a good balanced dataset. If your data is imbalanced, some number of images of particular class will be very high. Let's say in this dataset there are 100 number of classes. So these are the number of samples of 95 classes, and for this 5 class alone we have large number of data. So now eventually if you train your model using this data, your prediction will be very biased to these 5 classes. So this is not at all a good thing to have. So one thing what people do, they do undersampling. So what they do, they take few samples from each of these majority classes and balance with all the other classes. This is called undersampling. But this is not a good way to go. Why do you want your data to be low? You always want your data to be as high as possible. So we usually don't do this. What we do oversampling. So what oversampling is, you have that 95 low numbers of classes, and then you create copies of that particular data of that classes. So let's say if you have 5 images of cat, but you need 100 images of that cat, you keep copies, make copies of that images of those cats, and thus you increase the number of classes of your dataset. But can't create copies, same copies, because it won't be a good thing to do. You have to do data augmentation. So here data augmentation comes into play. How do we oversample your data? So I will explain you how to make those copies, because just making copies won't help. So this we call oversampling, and it's very much used during deep learning training. So data augmentation, I said that making copies. So how do we make copies? We can rotate the image, we can scale the image, we can flip the image, do translation or zoom into the image, zoom out of the image, we can increase or decrease the contrast of the image, we can add some granular noise into this image, and we can change the color contrast of the image. My idea is to not make copies which looks same as the image, but it has to look little bit different from the original image that you have. So this kind of operation that we do, we call it data augmentation, to make copies of a particular image which is of that particular object but shouldn't look similar as that object. So by doing data augmentation, as I have already said, we can balance class distribution. As we are making copies of that particular data, thus we are increasing the number of images in the dataset. Again, like someone questions about limited training data, this is how we tackle this problem. This is how we can increase the amount of data. Okay, so robustness to variation, like by introducing variation in training data to augmentation, your model become more robust. Okay, so let me give you a real life example. Let's say I am now talking, my face is frontal looking. So now if I give this image to the model, it will understand like it is me. But if I want the model to understand more, I have to give multiple profiles of my face. Like I will give 90-degree profile, 60-degree profile, upper profile, lower profile. Now, if I give this type of augmented images to the model, my model will be very much robust to any kind of variation of my face that will encounter. So that's how we can tackle this variation problem. Then domain adaptation is a thing like your training data is like in very good quality. It has beautiful color. Everything is perfect. But when you take your train your model in that data, and now you try to test in real life scenarios, real life data won't be that perfect. It won't be picture perfect. There will be variation. There will be different lighting condition. It will be dark. It will the images will be skewed. So by introducing data augmentation, we solve this domain adaptation problem. This problem is called domain adaptation when your test data differs from your training data. And then we solve the problem of regularization. So don't like get bothered about these like bombastic terms. These are very simple things. So we solve the problem of overfitting using this. Overfitting is when your data like is completely trained on your training data. But now you expect that when you test the data, the testing result will be very high. But it doesn't happen because your model is very biased to the training data that you have. But for test data, it is not giving good performance. That is called overfitting. With augmentation, we can solve this problem and we call it data regularities. So, yeah, any question?
Yes, sir. So we have one question. Is there any other advantage of data augmentation other than just increasing the number of samples?
Yeah, like as I have mentioned, you can make your model robust to variations. You can solve the problem of domain adaptation when you go into real life and test your model and have the like different kind of data, and you can solve the problem of regularization. So these are many like the main things that we solve using data augmentation. It's not just about increasing the sample. That is a one portion of data augmentation when you have limited number of data. But other things are these three topics that I mentioned.
Okay, I think your doubt is clear. So
Okay.
if you guys have any queries, please write it in the chat box.
Okay, so now I will explain this topic knowledge distillation very briefly. I won't go into deep because this is a very huge topic. So knowledge distillation is when you like compress your large model into a smaller model. So let's say you have data, but you don't have time to train on the entire data. You have a model which has been trained on this particular data already. So this model is pre-trained on this particular data. It has all the information of this data, but this model is huge. You want to employ this model into a smaller device like your mobile device, but you can't employ this because this model is huge. So what you do, you transfer the knowledge of this model into a corresponding small model. So this process is called knowledge distillation. And the architecture that we use is called teacher-student architecture. So teacher model is your larger model and student model is your smaller model. So you transfer the knowledge from this teacher model to student model. So there are many techniques to solve this issue, but I have just explained here what the overview is. I won't go into deep because this is out of scope of this talk. Okay. Now I will try to make you understand what my paper does. Uh, okay, anyone have any question?
So
Will
will the
knowledge
knowledge
distillation increase loss? Yeah, it will. Yeah, very nice observation. This model won't have as much accuracy as this generally, but we can solve this problem. But actually, we jointly learn this, so the loss will increase little bit. This is true.
then
But
hiding?
our motive is to reach to the accuracy as much as possible to this teacher model. Okay.
Okay.
Okay. So now let's try to understand this paper. It might look like tempting, but it is happening. I won't go into very deep, but yeah, let's try to understand this. So now I have been talking about semi-supervised learning, how to actually use semi-supervised learning. So now, see, this is the data that we currently have. So this is the label sample inside the data. The label is there where the object is. This is horse. This is unlabeled data. So these are football players. These are not. They are not annotated. They are not labeled. So we have this unlabeled labeled pair data. Now what I do, I apply weak augmentation and strong augmentation. Weak augmentation means very minor modification, very minor copy of that data. So I do weak augmentation, and you can see I just rotate like horizontally rotate the image. So this horse was in the face was on left. Now it is on right side. By strong augmentation, I mean I not only just change the orientation, but I also create these gray patches and remove portion of pixels from the image. This is called strong augmentation. So with my label data, I do weak augmentation. With my unlabeled data, I do weak augmentation as well as strong augmentation. And then I pass them to this teacher student framework, this knowledge distillation framework. This teacher model is already a pre-trained model. The task of this teacher model is to predict pseudo labels for this unlabeled sample. But what I mean by pseudo labels is I don't have labels for these samples, right? This unlabeled sample. I need labels to calculate the loss ultimately. So the task of this teacher model is to predict pseudo labels. The task of the student model is to generate predictions, and then we calculate loss using this pseudo label and prediction. This is very high level overview what we are doing. I am not going into details of what this label generator is, non-max suppression, adaptive. These are like very novel components inside the paper. I will not go into mathematical jargons also, but this is the very high level overview. How we have used teacher student framework, knowledge distillation framework, data augmentation into semi-supervised learning. So now if I show you like what is the benefit of doing this. So if you try to understand this graph, this is in y-axis we have MAP. MAP means mean average precision. This is a metric by which we try to measure how much good or bad our model is doing. Higher the MAP score, the better. So if you see, if we have supervised data, I mean we have all the data inside the dataset. By the way, this dataset is MS COCO dataset. It is Microsoft dataset of object detection. So if we train this model only with 100% supervised data, not with this framework, we get 37.9 MAP. But now if we utilize this framework, you see, with only 20% label data and rest 80% unlabeled data, we are able to surpass supervised performance with this framework. So this is how we have utilized labeled and unlabeled data and solved the problem of semi-supervised learning. This was our competitor paper, active learning. At 20%, they were at 35.49 MAP, but we surpassed the supervised performance with only 20% label data. So there was huge improvement. Okay. So there is a question why there is no backpropagation. Okay, very nice. There is no backpropagation in the teacher model because whenever we do backpropagation, we are tuning the weights and biases of that particular model. But as this model is already pre-trained, we don't want to play with the weights and biases of this model because it need to predict accurate pseudo levels for this particular unlabeled images. If we do backpropagation, we will mess around with its weight and it will be able to properly predict pseudo level. So that's why there is no backpropagation in the teacher model, only with the student model. Because at the end, the inference will be done using the student model only. I hope this is clear. Okay. Hmm. Now let me show you some qualitative results. Uh, Very interesting results we have. So at the very last row, this is me with my friends. This photo was taken in Domino's of Jalpaiguri only at my final year. So if you see like how capable the model is, it is predicting perfectly that we are humans. But there was this screen door, like glass window, and a cook of Domino's was making pizzas behind that. We as a human, it was very difficult to even perceive that information, but the model clearly predicts that there is person with like very large number of accuracy that there is a person who is making pizza inside that window. So I mean that was very surprising result. Again, like this is me in my bedroom with my friends. So if you see like this is small portion of the bed that is visible. The model is even able to understand this, like this is bed. So this is how capable currently the model is. So yeah, and we were like also submitted like this result into the paper, and the reviewers were also very happy to see this results. So yeah, this is I think this is the end of this topic, semi-supervised object detection. Yeah. So if you have any question, like you can ask, then I will move to the next.
So I don't think there is any
Okay.
questions. So,
Mhm. Okay. So the next topic is a very popular task, facial landmark detection. And I will briefly explain one of my paper, fiducial focus augmentation for facial landmark detection. This was done by us at Sony Research India and also with Professor Vinith Balasubramaniam from IIT Hyderabad. It was published in BMVC, British Machine Vision Conference at Aberdeen, Scotland, and we went there to publish that paper there. Yeah. So to understand this topic, we have to understand a topic called Siamese network. But let me first tell you, first let me explain you what Siamese network is. So Siamese network is a type of neural network which gives you similarity or dissimilarity between input images. So if you see this architecture, this is parallel CNN architecture. You have one image of cat, one image of dog. You pass it through the CNN architecture, and your task is to predict the similarity score. Obviously, these two are not same images, so the similarity score will be low. So this is the overall essence of what Siamese network is. I hope like this is very simple, but again I won't go into deep. This is a high level overview of Siamese network. Okay. So now let's try to understand what this task is, spatial landmark detection. So you have might have seen in like many Sony's mirrorless cameras, they have industry level autofocus. How do they achieve that? Previously, that was done using lenses, but currently they also employ AI models. So you have to properly understand the facial structure of the faces to properly do that, and that's when this thing comes into play. This
guys,
landmark
sorry
detection.
to interrupt. There is one
Hmm.
question. Why do we need Siamese network?
Yeah, yeah, okay. Just like bear with me for few slides, you will understand like why I have explained Sybase network here in this stuff. Because this thing has been used in paper. Yeah, just bear with me for a few slides. Yeah. So you can see the task is to predict these key points on your faces so that we can understand facial expressions. Let's say I might have shown you that lip sync task that I am currently doing. This landmark detection also involves there. Then I have told you about autofocus in Sony's cameras. Landmark detection is also being used there. So you can see like this is our method. We call it FIFA, fiducial focus augmentation. So you can see the landmark points are very accurate and quite uh, encompasses the entire face. But there is this paper, which is our competitor paper. For these corresponding images, they are not that accurate. I mean, you can see the points are little bit like outside the face, even for this and this also. So we have quite lots of improved from this competitor paper. Now let me explain you the methodology. I won't go into the architecture part again because that is again out of the scope of this talk because it will take another like seminar to explain you this. I will explain you this Siamese architecture, what the augmentation style that we have used, and what was the loss that we have used. So what the first our contribution was this fiducial focus augmentation. Just wait little bit. I will explain this in the next slide. You can understand by this architecture that this is Siamese architecture, just I have mentioned. So there are two different inputs, parallel backbone. So this is Siamese architecture. And our backbone network comprised of transformer and CNN backbone. Why we have done that, I won't explain here because this talk is not about explaining architectures. So I mostly wanted to focus on augmentation and Siamese training. So now let me like explain you what this augmentation is. So at the beginning of the training, what we do for all the images that we have, we apply standard augmentation technique that I have already mentioned. So if you see the face of this lady, we change the contrast of that image. We do that augmentation. That is soft augmentation that I have mentioned. And then we do hard augmentation. We create patches, patch, black, large patch, and like completely remove pixel from that face. So this is hard augmentation. So now you're done with this standard augmentation. Now comes into play our fiducial focus augmentation. So what we do, we create patches of small size of 5 by 5 around the landmark joints that we have. So these are landmark portion, and we create these 5 cross 5 patches at the very beginning of the training. And eventually, as the training moves, we train to reduce the patch size. So after let's say some epoch, some iteration, we reduce the patch size to 4 by 4. Then we make it 3 by 3, then 2 by 2, 1 by 1, and then we completely remove the patches around the landmark joints. This is how we train the model using this augmentation. Now the question arises, why do we do that? We do that because if we apply this augmentation at the beginning of the training, we are saying the model to focus on that particular landmark joints. We are explicitly saying the model, you need to focus on these parts, these black spots. So that's why at the beginning of the training, to give it a large confidence region, we are creating larger test size. But as the training progresses, now the model eventually understand where to focus on. So that's why we are reducing the focus region eventually. And at the end, we are completely like removing the focus region. So if you see, these are grad cam visualization. These are nothing but the visualization of the weights of the model, where it is mostly focusing on in the image. So at the beginning, you can see like the focus region is very high. This like excitement regions are very high. But as the training progresses, using this augmentation, the focus region is very skewed, very accurate. The model is able to predict this. Okay, so there is a question, what is CAM? It is called grad CAM. So it is gradient visualization basically. We have gradients inside the model. We visualize that on a plane to understand where the model is exactly focusing on. So this is not CAM, this is grad CAM basically. Yeah. So if you use our augmentation, you get this like very proper GradCam visualization. But if you do without FIFA augmentation, the visualization is not that good. The model is not able to focus properly. Uh, the thing that I have just mentioned has been implemented in code using this mathematical equation. Again, I won't go into deep in this. Okay. So now we employ deep canonical correlation analysis based laws here. Don't get worried. The name might be very like taunting. It is nothing but the covariance divided by root over the variance of the two features. So let me go back. Let's say you in this Siamese network architecture, at one branch you applied our FIFA augmentation. At another branch you don't apply our FIFA augmentation, only standard augmentation. Standard augmentation is in both the branches, but only in one branch you apply FIFA augmentation. You pass it through this backbone. Non-FIFA augmented image, you pass it through this backbone. You get these features. Now we have to predict the similarity and dissimilarity between them. So that's why we apply the DCCA laws. Why we apply DCCA laws? The characteristic is very simple. It calculates the covariance between the two features. So covariance is if one feature is similar to one, it will move into same direction in a space, in an Euclidean space, basically. So covariance is very simple that we have learned in our engineering days. That is simple covariance like that. Okay, there is a
Other,
question.
so
Why
why
do
do
we need to reduce the patch size step by step, not all at once? Okay, very nice. So yeah, so let's say if you do this all at once, at the very next epoch, the model is being trained, it will completely get out of control, like where to focus exactly. But if you do this eventually, no, so the model still knows like what to focus on. So it's like the drinking a cup of hot tea suddenly and drinking a cup of hot tea like by making it colder step by step. It's just like this. Like deep learning is all about like mimicking real life concept. So that's what we have done here. I hope this answer your question. Okay. Yeah. So I have explained you, I think, covariance. It's all of your engineering students, so you're well aware what covariance is. And again, variance is. So variance is like distribution of the data from particular point. So if as we are sending practically the same images to that model, but with different augmentation, we hope the correlation value between the two features to be very high. But to use this correlation as a loss, we can't use it directly because our loss has to gradually decrease when the model will train. But as eventually the model will get trained, the correlation will get increased. So how do we use that? Very simple. We just use negative of that correlation. So that's how we implement this DCCL loss and calculate the correlation between these two features. So yeah, this was the overall contribution of this paper. I have not gone into the architecture. So these are the some results. These are very popular datasets, 300W, CFW, FLW datasets. So these green points are our results, and these red points are competitor papers results. And I don't think I have correctly zoomed in, but our results are very much accurate rather than the competitor paper. Now there are some failure cases too. So the reason for the failure cases may be extreme head profiles and very huge occlusion of those faces. Like you can see, barely the face is visible in these images. So these blue points are the ground truths and the green is our prediction. So it has not been able to properly predict because of this like extreme occlusion in the faces. Another instance is when the face is very zoomed in, not entire face is visible. Like this face of Michael Jackson, like it's very zoomed in, and even his eyes are not visible because of these sets, because of these glasses. So that's why like it has not been able to properly predict the landmark in eye region. Again, in this face, the face is like very zoomed in. This extreme profile, like 90-degree profiles, where you have to predict the landmarks. So these are some failure cases. Again, when two persons are there, so this jawline portion is not at all visible. So this is another issue. And even like there are some objects on your face, like in this case, the hand of this person. So at that point also, the model is not being able to properly predict. So these are some failure cases of the of our network. And if any of you want to work on this topic, so these are the cases like you have to tackle to make a good paper out of this or move the research forward. Yeah. Uh, yeah. So I think I have completed all the presentation that I had. So you can connect
So
with me in Instagram or LinkedIn. Like I'm very much active in this platform. If you have any question, you can ask me there. Yeah. And now we can start the Q&A if you have.
if you have any queries now, you can ask. I'll be sharing the LinkedIn and in the chat box. I have shared the LinkedIn. So you guys have any queries? Please ask them.
Okay. How do I start learning deep learning? Okay. Yeah, this is a very daunting question actually. Uh, can I know in which year do you have so I can have a curated answer for this? Okay, third year. Uh-huh. Okay, someone is from first year. Okay. Okay, let me give you a very straightforward answer. So if you like most of people what they do, they go to Coursera and start learning the course of hand. But I didn't do that. because like I find it didn't help me a lot. So what I did, I started from paper reading actually. So I go into top-down approach. That's why I've explained you this topic in this way. So take a paper, understand what concepts are used in that paper, and try to go deep into them. So eventually, like this is research field only. Deep learning is constantly evolving. There is no particular answer to any particular question. Today, I have done facial annotation in this way. Just 1 month after this technology will be obsolete. So it is an ever-changing field. So you have to constantly read like good research papers and understand the topics what there are. And you have to be very good in implementation because if any idea stuck into your brain, you have to implement them. Okay, can I start learning deep learning directly without learning? Yeah, I actually did this. So, like, I didn't start with machine learning. I did deep learning first. Then, when I needed to understand like nuances of topics, I went into machine learning. So, you can very much do this. Very much agree with this point. Like, you can start deep learning without machine learning. Yeah, you can very much do this. Yeah, but again,
I
you have to
mean,
know how to read papers and understand them. Okay, what are the resources to learn email DL step by step? Okay. One very good resource can be like there is free courses on YouTube of CS231N from Stanford University. So actually, Dr. Andrew Karpathy took that course with Fefe Lee. Andrew Karpathy was the head of Tesla's automation team. So you can go through that course. It's very good thing to start with, like CS231N 2016 spring course. You can go through that.
so one more question is that how much Python I have to learn for ML?
Very much. I mean, like you have to be proficient in Python actually, because all the frameworks that we use mostly are PyTorch. We don't use TensorFlow. PyTorch is completely based on Python, so you have to have ample amount of knowledge in Python. Yeah. So I think if you are in first year, you have ample of time to learn Python and then learn this PyTorch framework. I won't suggest you to go to learn TensorFlow because it is complex, cumbersome to use, and we don't usually use that now. So yeah,
So
learn Python, then learn PyTorch. Yeah.
how much we need to learn DSA for machine learning?
Not very much actually, but during implementation, you need the concepts of some DSA, but you don't need to solve like those coding problems and all. That very high amount of knowledge in DSA is not necessary. In this field, deep learning, your analytical skill is more important. How do you solve theoretical problem and then implement it into practical? So your analytical skill should be very high. Like you have to be proficient in maths and probability. So DSA is important, but not that much. Yeah.
So I think there is no more questions. So thank you Dada for joining. The session was insightful for me personally, and I think it was helpful for you all guys. So thank you.
Okay. Yeah. I mean, if you have any question, you can connect to me in LinkedIn or Instagram. Any other question, I will be happy to assist you.
Thank you, Anna.
Thank you. Thank you. Bye. Have a nice